So good morning everybody. It's very nice to see that some people still could climb here after this great dinner. So thank you for the organizers. But now we will go on, and today we have the first talk. So my name is Kai Myrberg, I'm from Syke. And the first talk is a keynote talk by Hans Bies about a new non-hydrostatic coastal model for simulating waves of the Baltic coast. So please.
Thank you very much. Thank you very much for the introduction. Okay. Yeah, so today I want to present a bit more numerical topic. We are working on numerical wave modeling, and yeah, you can see on this slide here we are developing open source software called Re3D at NTNU. We have started with a high resolution model, a CFD model, where we can go really close to the structures, and then over time we saw we need to have better wave boundary conditions, so we started to build a shallow water equation model, and then afterwards a fully nonlinear potential flow model, FMPF, which we have used a lot, and it's really tailor-made for Norwegian conditions where the water depths are really large. I'm going to show this a bit later, how it looks there. And so FMPF works really well as a large-scale coastal wave model, but in order to tackle the challenges of the Baltic coast, but also other coastal areas, we decided to go for a new wave model, a non-hydrostatic Navier-Stokes equation model. So our framework has the capability, on the one hand, calculate the waves and the current, but on the other hand, there's a lot of other additional physics, like, for example, porous structures, vegetation, floating structures, but also, in this context, very important, sediment transport. So, yeah, what you see here, we always highlight that a bit to show the differences between the conditions we work in and what maybe around the world people are working with when they think about coasts. So we have the typical North Sea conditions driven by the tides, very shallow water. And then on the right-hand side, you can see the Gulf of Finland. This is what this conference is about, where we have average water depths of 50 meters. And then on the next slide, you can see what we think is a typical Norwegian condition. This is Bjørnafjord. It's a location for the floating bridges for the E39 connection. So this is one of our research topics there. But you can see on the right-hand side how deep trenches, there are very deep trenches in the fjords, up to 600-meter deep, right? And that makes it very difficult for typical coastal wave models to tackle this. And on the other hand, where there are spectral wave models like SWAN, we have seen this yesterday, they would struggle with the diffraction. So in the Norwegian coast, we have a lot of islands causing a lot of diffraction, and so the waves are not fully blocked, but just diffracted around the islands and continue to propagate. And this is why, for a coast like this, it's also very important to consider phase-resolved waves. On the next slide, you can see the simulation with the potential flow model. So this is on a scale of 35 by 45 kilometers. And you can see how the waves then, we have the swell conditions, how they would propagate towards a coast like this. And because we have a huge change in seafloor elevation towards the entrance of the fjords, there's a lot of activity there. Then the water depth is increasing again, so we're losing a lot of wave energy there. But a lot of variations in seafloor elevation, a lot of diffraction. And then if we go to a model that would be more suitable for Baltic coast, we have much more mildly sloped beds. Like I said, up to 50-meter water depth, so quite a bit different. And that's why we went for this new model. We want to be able to model waves. We are still talking about 50-meter water depth, so need to think about dispersion properties. But on the other hand, the processes directly near shore at the coastline are really important. So we need to have a wave model that can also represent the run up and run down, the wetting and drying, the breaking wave mechanisms there, which are driving the sediment transport processes. Yeah, so just to give an overview over the types of models we have developed. All the way down, we have the high-resolution model. It's a three-dimensional model. It's computational, very expensive, so that's the drawback with this model, but it can capture all the physics. But to use it for coastal modeling, it's just too expensive for that. If we maybe go to the top model, it's a shallow water equation model, so it's a 2D model. And then it's limited by the fact that it can only handle dispersion up to certain KD values. You can increase that by adding other terms, Boussinesq terms, for example. But in general, it also is 2D. That means having the 3D effects at the coast is not possible to capture with this kind of model. Then I've showed a bit about the model we have developed for the Norwegian coast, the potential flow model. It's very efficient. It can capture waves from deep water to shallow water. But the problem here is that we are missing the viscous effect. So all these coastal processes, when waves and current are interacting with the sediment bed, it's not possible to capture. So then the new model is as efficient or close to be as efficient as the potential flow model. But in addition to this, we also can have the viscous effects inside. We can then also in the future calculate sediment transport, for example. Yeah, I'm just showing here the governing equations. So for this new model, NH flow, a non-hydrostatic model, we're solving the full Navier-Stokes equations, continuity, momentum, and then the free surface elevation is being calculated by integrating the continuity equation over the depth. And this is maybe in contrast to what we can do with the high-resolution CFD model, where we can look at two phases. We can look at the overturning crest of a breaking wave. With this type of model, that is not being directly captured, but we can represent kinematics of a breaking wave. This is the numerical representation, how we are solving the equations. And yeah, just maybe the important part here is that we are solving this in a conservative way. And we use a Goodenough type scheme with a Riemann solver. That means it is shock absorbing, and that gives it very nice numerical properties when it comes to nonlinear situations or also breaking waves. The model is being solved in a parallel fashion. So on the right-hand side, you can see how we are splitting up our meshes into smaller pieces. And then we have a communication between those sub-processors, so we can run simulations on supercomputers or on computers with several cores and really go to larger domains because of this strategy. We are using Hyper's solver library. It's an open source solver library to solve the systems of linear equations, and that has proven to be very efficient for us. Yeah, NHFlow uses a so-called sigma grid. It is a simple transformation in the vertical direction. So the idea is that the bottom grid line follows the bed topography, and the top grid line will follow the dynamically moving free surface. And then having the transformation inside the discretization, it's a very straightforward way to calculate and solve the equations on a sigma grid. And then coming to the wetting and drying dynamics, so we want to be able to model waves that are running up and down the shore. And I made a small test case to show the properties of this model. You can see this is a conical island. It's scaled up by 5 times to make it a bit more visible. So we are just generating some waves. There's a reflective wall, but you can see the kind of dynamics this model can handle without any filter or stabilization. I think it's quite interesting if you compare this to different approaches. So you can calculate the run up, run down, and for the braking, it's no additional treatment added to this. So when the waves get very steep, this Riemann solver with the shock absorbing capabilities keeps the solution stable. And we did a lot of validation already on this model, and we put this a bit into context to other non-hydrostatic models in the community. Probably one of the best known model here is SWASH, developed by TU Delft. And in contrast to what we do, they use the primitive variables, so it's not the conservative form of the Navier-Stokes equations, and they have some pressure correction method inside and surface correction method inside. So for relatively coarse meshes, they can represent the dispersion in a really good way. So we are just running here second order Stokes wave with a KD of 2 pi. So we have a water depth of 6 meters and a wave height of 6 centimeters. And we just let the waves propagate and test the dispersion characteristics of the model by comparing it against the theoretical values. So after 100 meters, we compare the theoretical wave gauge with the numerical results, and if the model can capture the dispersion, it should be following the theoretical values. And yeah, you can see an NH-wave, which follows or was inspirational for what we did using the shock absorbing method. They are not using a pressure correction method, which leads to a slightly worse dispersion than what we can achieve. We need a bit more cells than SWASH, but our initial tests show that when we go to 3D meshes, larger domains, we are quite efficient in comparison. Yeah, one of the very well-known tests in wave model validation is Beijing-Battier. So waves are propagating towards a shoal. So we have a shoaling area, then there's a flat bar, and then on the flat bar the waves start to decompose. So we have linear waves propagating to the submerged bar, and then because of the change in bathymetry, they are decomposed into the higher order harmonics. So we get shorter waves, higher frequency waves, and that makes it quite difficult now because the KD value goes up quite a bit in this region. Maybe I just show how this looks like. So you start with the linear waves, then the waves are shoaling, and then on the flat bar and also on the downslope, the waves are decomposed, and you can see how the wave field behind this bar looks quite, lots of activity there. So we're running this case, it's a 2D test case for us. This is simulation is 50 times scaled up to make it a bit more visible. 1,400 cells in horizontal direction for the 35 meters of this domain, and we use 2 vertical layers to calculate good pressure dispersion there. Then we can compare our numerical model results with the measurements. We have 8 different gauges in this test case. So the gauge 1 would be the undisturbed linear wave. I think it's a second order Stokes wave. I'm saying linear, it's second order Stokes wave. And then you can see for the gauge 2, it's at the end of the shoal. We have shoaling, that means wave height is increasing, wave gets more nonlinear. And then at gauge 4, which is in the middle of this flat part, you can see the additional peaks to appear. And then when you move further towards gauges 5, 6, 7, 8, the higher order harmonics are appearing, and you can see that the model can capture that quite well. Then we were looking at another well-known test case by Ting and Kirby. They have used waves propagating on a mildly sloped bed, and they have basically 2 test cases. One where they are creating spilling breaking waves with the shorter waves, and in this case what I'm showing here is the longer waves with the 5th order stenoidal waves. So it's long, or it's a non-linear shallow water waves, and then in the experiment the waves are plunging breaking waves. And you can see here in this simulation how the waves are being represented in our model now. We don't see the overturning crest, but the kinematics of the breaking. That means we have the shoaling, we have then, because of the breaking, energy dissipation that is represented in this type of model. But you also see how the waves are running up and down on the beach, and that mechanism is represented in the numerical model. So we have, in this case, 4 different wave gauges. 1 and 2 are before the breaking, and then you can see gauge 3 is just before breaking, and 4 just after breaking. And we compared the measured and modeled waves, and you can see how the model can capture the shoaling quite well in wave gauge 1, and there's some deviations in the other gauges, but the general picture, it's quite close to what is happening there. So I have now some real-world cases where we use the new model. This is the Naissaare harbor in Estonia, and yeah, we are generating short-crested waves propagating towards this harbor. You can see the breakwater on the right-hand side, and yeah, we have a significant wave height of 1.4 meters, wave period of 10 seconds, and then we are using irregular waves with a short-crested approach. It's a mesh with 800 times 600 cells, and we now need to use 5 vertical layers. We have irregular waves, so we have different wave periods in this wave field, so we need to also be able to capture the shorter waves. So in overall, it's 2.4 million cells. And yeah, you can see the simulation here. The waves are propagating towards the coast. Then when they are almost near shore, you can see how the waves are shoaling. Wave speed is reduced, so you can see how they are then moving towards the coast due to shoaling and refraction. And also the effect of the breakwater, maybe a bit, I don't know whether you can see that as well there, the diffraction around it. And then we placed different wave gauges. So for this case, we don't have any measurements at the moment. So we are placing different wave gauges at different locations, which are important to understand how the breakwater is working. So for the harbor, you want to have as calm conditions as possible. And with this model that can capture the diffraction, you can then estimate the wave conditions inside the harbor. So we have wave gauge directly in the generation zone, so we have the wave spectrum as it's being created. And then we have 2 wave gauges outside the harbor and placed 3 gauges inside the harbor for comparison, just to look at the relative significant wave heights inside and outside the harbor. So you can see how the significant wave height is being reduced towards the coast due to the breaking there. Yeah, we can see we get wave gauges 4, 5, and 6 are the ones inside the harbor, how the wave energy is significantly reduced for what's happening inside the harbor. We look at the different wave spectra to look at that. Yeah, wave gauge 1 with the generated waves, and then in comparison the other gauges. What's I think interesting here is wave gauge 6, so we have the peak significantly reduced. That's the top image on the right hand side, and then we can see the low frequency part, low frequency oscillations inside the harbor. So that's where we have additional components coming in for the wave gauges 5 and 6, so we can see this kind of harbor oscillation is being captured as well. Yeah, just an outlook. We are working currently on this part at Pärnu. Yeah, I think we have seen the results yesterday already for this part of the coast. What we want to do there, we want to combine the waves, the current processes with the sediment transport. Maybe I just start the video already. So we have started to put everything in place, manage all the data, and started to simulate the waves at these locations. So this is here the river outlet being modeled. You can see the diffraction and shoaling effects of the channel coming from the river, creating this wave pattern at the outlet there, and then how the waves are propagating towards the coast. Somehow the video is a bit stuttery, but I think you can see what's happening. And inside the channel, water depth is a bit higher. That's where we get the lower wave heights. I just want to show also a bit other possible applications of this kind of model. We have another EEA project together with a Portuguese partner. It's a much smaller project, but it's a fun project, I think. It's about surf waves. This is the coast at Ericeira, close to Lisbon, and it's a unique location for surfing, probably Europe's best spot for wave surfing. And so we are using there this new model to predict the waves, how they're propagating towards the coast, because today there's not a real tool to estimate or correlate the wave conditions out in the sea and the actual wave conditions on the beaches. So this is today all based on experience. So how would this look like? We have It's a bit stuck now. Can I? All right, thank you. Okay. So here you can see the coast of Ericeira, and I start. No, okay, it doesn't want to do this. And we have modeled this coast, and I think it also shows the possibilities with this kind of model. It's 9 by 9 kilometers, resulting in 9 million cells, and it's still something that we could run on a laptop. Run for a day and get 2 hours of simulation time. So it's still very efficient. So it's quite high waves compared to what we have seen for NICER. For example, we have here 4-meter wave height with a 12-second period. This should be a movie, but it's not playing, so maybe we just jump further. So there are different beaches at this coast, and one of the most well-known is the Riviera de Ilhas, and this red box is the zoomed-in area where we can see now on the next slide how the waves are propagating towards the coast, and now you can capture the shoaling and then also the breaking areas. So we think it could be a very nice tool for giving reliable wave conditions predictions for this coast. So we see quite some interesting applications for a model like this. So coming to the conclusions, so we presented a new hydrostatic model. We can see very good dispersion. For the test cases we run, we are including a dynamic coastline. We have wetting and drying inside. The breaking waves are being handled in a stable way. And if we look towards what we want to do in the future, we want to combine it with additional physics, and especially sediment transport, something that we're interested in the context of the Baltic coast. And thank you very much for your attention.
Thank you, Hans, very much. I'm sure that there are some questions from the audience. I have at least one question. This drying and wetting points, it looks very fancy for me as an old modeler. That how you keep this model stable in this situation? Can you tell about it?
No, the wetting and drying is quite straightforward. You're just looking at the water depths. If you put in a critical value, which is very small, maybe 0.1 millimeter, and if the water level falls below, then the cell is identified as dry and just excluded for that time step. When there's water flowing in again, then the water level goes above this critical threshold, and then the cell is active again. So this kind of wetting and drying, I think it's quite like most models do this.
But can you have only one dry point in between wet points, or vice versa? Then you have very difficult boundary condition if you have only one point.
Yeah, I think the great thing about this wetting and drying algorithms, you don't have to explicitly treat any boundaries.
Okay.
So just, okay, if you have this interface, then the model would automatically detect it.
Okay.
So it's not no additional boundary conditions, and that's really the nice effect.
Pentti.
Thank you. Very interesting presentation. As you know, I'm not expert in hydrodynamics, CFD, but ice. But in naval architecture, the big challenge is turbulence. How you model the turbulence? Do you have a similar any turbulence modeling in these breaking waves, or?
Yeah. So right now we are not adding turbulence, but since it's a Navier-Stokes equation, that is the foundation here. In contrast to the potential flow, we will also add the turbulence model and will be captured. I mean, turbulence, of course, always is a question of resolution. Like if you think about a ship, we need to go down to boundary layer resolution. So that's not the focus of what we want to do here, but we think more on ocean currents. We have recirculation areas, so that's going to be important. But also when we think about sediment transport, we do have a roughness on the bed. So that will be quite important to capture. But I think it's maybe a different level of resolution compared to ship hydrodynamics.
Yeah, because like a propulsion, we have in propeller, it's very important, the turbulence, but it's a different problem, I think. Yes.
Yeah, exactly. So then that is really down to highly resolved flows, and I think that's not what we want to do here. If we need to do this, then we have the CFD model, which could be used for that. Yeah.
Thank you.
But it comes at a price. You have to resolve everything. So.
I learned that it's a very complicated problem. That's what I know.
Yeah.
Thank you.
Okay, do we have other questions to Hans? Kevin.
Thanks, Hans. Back in 1993, there was quite a well-known paper at that time, which would be far too long ago for you to remember, but the older among us may, that said that in the next 20 years, and the paper was designed to try and look forward, there would be no progress made in modelling of a wave at the point of break. We can do it up to it, we can do it after it, but not at the point. We're now another 10 years on in the future. How is modelling of the actual breaking point progressing?
Yeah, I think it has been, like in the last 10 years, there's been a lot of progress, I think from especially 2010 on. There has been a lot of work on the 3D numerical wave tanks, CFD models. So we've also done quite a lot of research where you can resolve the breaking wave using two-phase flow. So you have water and air in your simulation, and then you use like interface capturing in between, so you can actually model the overturning crest. But when is this important? What we see is it's really important. So it was really a big goal to be able to do this, but when you are then able to do it, then you see it's important when you have breaking wave loads, maybe, or if you really want to look at the processes in detail. But when we look at the larger scales, a model like I showed here, where it's not resolved, but the kinematics are included, then everything you need is there. So it's kind of, you can do it, you can resolve it, but again, it comes at the price. You need to have a much finer mesh, and you need to have smaller time steps to capture the physics. So yeah, I think it's possible today, but now that you can do it, probably people have done it, and it's not so much the thing you go for, I would say. For engineering applications, at least, yeah.
Okay, are we on other questions? I don't see any. Thanks, Dan.
Yeah,
Hans,
right.
very
Thank you.
interesting presentation. And the next paper is by Ville Junttila and the co-authors about Finnish-Estonian collaborative research project utilizing passive samples in pharmaceutical research in the Gulf of Finland. So please.
Thank you. Hello everybody. My name is Ville Junttila and I'm from Finnish Environment Institute. And I'm going to talk you a little bit about pharmaceuticals and our research project which we are doing together with our Estonian colleagues. So, as we all very well know, the pharmaceuticals are very crucial for well-being of our societies, but those beneficial properties can also turn harmful when these compounds are entered to the environment. And these pharmaceuticals, they are designed to have an effect, so this makes them biologically very active substances. And although most of pharmaceuticals are not most persistent compounds, their flow from the communities to the environment is typically almost continuous, which leads to their constant presence in the environment, making them so-called pseudopops, or persistent organic pollutants. And pharmaceuticals have also been noted to accumulate in the food chain, which extends their effects beyond aquatic organisms. And it is also widely acknowledged that more information on the occurrence of pharmaceuticals and the risks they pose is needed in the Baltic Sea region. And this is why the updated HELCOM action plan includes 3 actions specifically addressing pharmaceuticals. And one of those is to improve the knowledge base about occurrence and effects of the pharmaceuticals and ensure this information for the expert community by 2025. Well, how much information do we then have about pharmaceuticals in the Baltic Sea? For this presentation, I conducted a quick literature review to assess the quantity of scientific publications on the occurrence of pharmaceuticals in the Baltic Sea. Well, this is not the complete picture, but the left side map shows that indeed studies have been conducted, and especially in the southern Baltic Sea near the coasts of Poland and Germany. And in addition, more comprehensive surveys covering almost entire Baltic Sea have been done, as shown in the right maps. And apart from these, there is also some grey literature, such as governmental reports and other non-peer-reviewed studies. And all these studies indicate that the presence of pharmaceuticals in the Baltic Sea environment is very extensive. And especially near cities, certain pharmaceuticals can pose risks to the well-being of marine environment. Well, although some of these studies have collected a significant number of samples, the number of sampling events has generally been small. So in other words, these results only provide information on momentary concentration levels of substances that happen to be present in the water at the time of the sampling. So to obtain a comprehensive picture of prevailing concentrations with crab samples, a large number of samples usually need to be taken. If we want to, for example, assess the average concentrations levels over a year, around 8 to 10 samples usually per site needs to be taken. And this high number of samples, in case of hazardous substances, 10 samples per site is considered high number of samples. So this means also increasing costs. And in case of pharmaceuticals, this can pose challenges as their analysis is usually very expensive. And also the one drawback of crab samples is also that the environmental concentrations may be so low that analytical methods cannot detect or quantify them, and yet these concentrations can still be significant for the organisms that are exposed to pharmaceuticals. So one solution for this problem could be the use of passive samplers. And these passive samplers are devices containing collective medium, and this medium binds substances from the surrounding water, which can then be analyzed in the laboratory. And based on the amount of substances that are accumulated in the samples, the average diluted concentrations in the water during the deployment time can be estimated. And with sufficiently long deployment time, even very low concentrations can be detected, and additionally those substances that may not be consistently present in the water can be also identified. These samplers have been designed for various types of substance groups, such as for pharmaceuticals, but also for PFASs, pesticides, metals, etc. So in our study, we are deploying these passive samples along the coasts of Helsinki and Tallinn, as well as in the open sea of the Gulf of Finland. And this sampling is conducted 3 times for 3 to 4 weeks each time, which provides a total of 2 to 3 months of data collection on pharmaceuticals in marine waters. These samplings are carried out in the fall, spring and summer to account the variation in pharmaceutical use during different seasons, and also to account the changes in environmental conditions. For instance, allergy medications are more commonly used in the summer, and thus their concentrations in the environment have also noted to be higher during that time. And in summer, the conditions are usually more favorable for biodegradation of pharmaceuticals compared to fall or winter. So we have chosen 3 sampling sites in both countries, and also one deployment will be conducted somewhere in the middle part of the Gulf of Finland. So our study is one example how these resource vessels can be used in transnational monitoring studies. And we are studying locations that should not experience direct pharmaceutical loading, as well as clearly loaded or diffusely loaded areas. So in this way, we can see if these substances can be found from areas where you would not expect to find them, and we can estimate if other pollution sources than wastewater treatment plants exists. And finally, our project aims, of course, to provide information on the occurrence of pharmaceuticals and to support the state assessments of the Gulf of Finland and the full Baltic Sea. So this is direct input to the Baltic Sea Action Plan. And we also provide experience and guidance in the use of passive samples in future monitoring studies, so this could be utilized more widely. And of course, one main goal is to foster collaboration between Finnish and Estonian researchers, and that's what we have been doing here during this great event. So we will continue our research, and hopefully an opportunity will arise for us to present our actual results in the fall of next year. So thank you.
Thank you, Ville. Any questions from the audience? I have at least one question about these pharmaceuticals. Where they come to the sea? What are these substances which are called pharmaceuticals?
Well, most of them comes from our everyday use, of course, via wastewater treatment plants, but also agriculture, fish farming, our leisure housings are sources for these compounds.
Okay, any more questions? Yeah, here, please.
Thank you for the presentation. Actually, I mean, maybe a couple of years ago, I had experience with this passive sampler. We use this to measure some pharmaceuticals in surface water in Estonia as well. Well, I just want to ask, do you experience any loss of your sampler during this installation in open sea, and how do you handle that?
Did you ask that, did we lost
sampler? Did you lose any of your sampler?
We are doing our first sampling round Currently, we have collected our Finnish samples and the Estonian samples are still in the water. We missed 1 point. I don't know why. Maybe it was due to lack of my knot making skills. Maybe it was pirates, but anyway, we lost 1. And this is one drawback with these passive samples, that if you lose 1, then you lose lots amount of work and information. And these are maybe little bit more expensive to take these samples compared to crab samples, but yeah. Please, can you repeat?
In which water depths those samples are?
We are trying to get them at the middle depth, so at the coast, if typically near the Helsinki, the depth is something 8 to 10 meters, so middle depth.
I apologize if I just missed something, but what's the output? Is it just presence absence? Is it some integrated value, presumably not concentration because it can't keep going, but what's the output units, I guess?
Yeah, based on the amount that is accumulated to the passive samples, we can estimate that what has been the average concentration in the water during the passive sampling time. And this can be done for some compounds. For some compounds, we need more information to estimate the accumulation rates, but for some compounds, this information already exists, and we can estimate the average concentrations. And then compare to them to the harmful concentration levels to do the risk estimations.
If you have a real problem with losing the samplers and the buoys, I suggest you use a benthic release system and rig the whole thing so that the sampler and the buoys are at the depth of 10 meters or wherever we want to put them. And then once you want to retrieve them, you go out there and put out the hydroacoustic release, and they pop, they come to the surface. And for this we can use Aranda, we can deploy those things for you and we can collect them.
Okay, sounds good.
Any more questions? Okay, here.
Yeah, hello. Thank you for the great presentation. I would like to ask if these pharmaceuticals, they are accumulating in the ecosystems and possibly very negative effects will occur. What kind of strategies of policy implementations of such, do you know, are there now implementing or?
Well, that's a little bit difficult question because, of course, we can't go to tell people that you should stop using pharmaceuticals, medications. But I guess that improving the wastewater treatment techniques will be one solution. It will be required in the future to clean more micro pollutants from the wastewater, and also we can educate people that please return the unused pharmaceuticals to the pharmacies. Do not throw them to the waste or flush them in the toilets and that kind of thing.
Thank you.
Yeah, Jukka.
To answer your question, there is now Water Framework Directive. The EU priority substances are now under revision, and there are candidates, new substance candidates to be proposed by Commission, and they include several pharmaceuticals. And if this directive proposal will be approved, there will be binding maximum concentrations of these pharmaceuticals allowed in surface water. And by that way, it improves its possibility that the emissions has to be decreased for these pharmaceuticals. But it's still proposal, but looks like these pharmaceuticals will be included to the directive.
Okay. I don't see any more hands, so thank you, Ville, very much.
Thank you.
For this interesting presentation. And now we have the next by Katri Viigand and the colleagues about evaluating the vulnerability of the shores of the Eastern Baltic Sea with respect to extreme water levels. So please.
Good morning, and thank you for the introduction. The risks and damages associated with coastal floodings are a large concern of low-lying countries with extensive nursery areas. And the impacts of severe flooding events include loss of infrastructure, extensive coastal erosion, loss of land, and even loss of life. The modeled annual maxima in the Eastern Baltic Sea has shown a remarkable increase, and the increase has been the highest in the eastern Gulf of Finland and in the Gulf of Riga. And this pattern leads to the question, what is behind this kind of increase of extremes, and is this pattern going to continue, and how it will be spatially distributed? The local water level in the Baltic Sea is a combination of joint impact of several drivers that follow different probability distribution, and the presence of various distributions generates different levels of exposedness and vulnerability for low-lying coastal areas regarding to extreme water levels and their return periods, and a longshore variation of the shape parameter of generalized extreme value distribution may prove itself as a helpful tool for classifying the coastal segments by the likelihood of experiencing higher extreme water levels. To explore this, we used modeled and observed water levels. Two sets of modeled water level data are extracted. First is extracted from the Rossby Central Ocean model, and this temporal resolution of this is 6 hours, and this covers years 61 to 2005. Second set of model data is extracted from the RCA4 NEMO, and it has temporal resolution of 1 hour, and it covers years 61 to 2009. And they both have spatial resolution of 2 nautical miles. And we cover, our study area is shoreline of Lithuania, Latvia, and Estonia. Altogether, it covers 351 grid points. And model data we complement with the observations from 14 sites along the study area. To estimate the extreme value parameters of water level maxima, we used the largest value that occurred during the calendar year. And this, in the conditions of Baltic Sea, these values may be correlated to the impact of clusters of storms that may appear, that elevate the background water level of the Baltic Sea and may appear in one year of December, and the same event may continue in next year, January. And to avoid that kind of correlation, we use another set of maxima over the stormy season, starting from July of 1 year and ending in June of subsequent year. And from this, we construct the ensemble of projections, and these projections we use to construct the ensemble of parameters, and the parameters we apply to construct the ensemble of 40 different projections of extreme water levels and their return periods. And for this we use these 2 different circulation models, different sets of block maxima, these annual and stormy year maxima, and also different methods of calculation of extreme value distributions. And this ensemble we apply to find estimate of 50-year return period for extreme water level values for our study area along the coastline of Baltic states. And if these block maxima are independent, then they should follow the generalized extreme value distribution. For this distribution, we find three parameters: the location, scale, and shape parameters. And the shape parameter plays a central role in these projections. If the value of the shape parameter is negative, then this generalized extreme value distribution turns to Weibull, the three-parameter Weibull distribution. On the figure, it's a red line, showed with the red line. And Weibull distribution means that projections for the future have slow increase in time. But if the shape parameter of GEV is positive, it indicates the Frechet distribution. Frechet distribution is blue, showed on the figure with blue line, and in this case the increase of extremes for the higher return period is much more rapid, and many more dangerous floodings may occur. And if the shape parameter is 0, it indicates the Campbell distribution. This is green line, and this is the increase of extremes between two previously mentioned distributions. So if we compare the estimates calculated by different methods for this GIV parameters, for a shape parameter, the scatter is extensive. And this means that the straightforward use of Campbell distribution for extreme water levels is not justified. Usually in our region, in this east coastline of Baltic states, Campbell is most commonly used. And the different estimations for GIV shape parameter in the most of coastal regions do not match well, but the average of these estimations changes its sign several times along the study area, crosses the 0 line. It's maybe not perfectly visible everywhere here, but the average is below 0, negative in the coasts of Baltic proper shores on the left side of the figure, and also at the west of the Tallinn until Sõrve. And the average of GIV shape parameter is 0 in most of the areas in Gulf of Riga, except Pärnu region, and also in some points of open shores of West Estonian archipelago and at a part of the northern coast of Estonia. And this parameter is positive in Pärnu and at the end of the Gulf of Finland. And also the match between the estimates calculated based on modeled data and based on the recorded data varies remarkably along the study area. The match is better with recorded data in Latvia than in Estonia. The GIV shape parameter based on one projection, the RCO data, varies substantially along the study area. And here are visible that the points marked with red should follow the Campbell distribution, and there the increase in extreme values in time should be slow, but still existing. And the points marked with blue follow the Frechet distribution, and in these regions the increase in extremes is rapid, may be rapid, and these are more prone to extensive floodings in the future, these areas. And the points marked with yellow should follow the Weibull distribution, and they show the slowest increase in extreme water levels in time. And the spread of the projections of extreme water levels that would occur once in 50 years is almost constant. It's 40 centimeters along the entire study area. And the appropriate projections of extreme water levels can be obtained as a weighted average of the ensemble members. And the resulting return periods are higher in the bayhead, like in Pärnu region, and also in Narva-Jõesuu, in the bayhead of Gulf of Riga, and lower at the open part of the Baltic Sea, at the coast of Lithuania and Latvia and West Estonian archipelago. And we also watched the GeoShape parameters for the water level minima. And in case of minima, the negative surges are formed slowly during high atmospheric pressure and offshore winds, and they persist for a longer time. And because of that, they have a totally different timing of water level maxima. They occur in summer. Therefore, the minima found over stormy season, starting from July until June next year, may be highly correlated and is probably not usable in this case. But as a result, the GeoShape parameter values along shore are mostly negative, and this reflects the presence of 3-parameter variable distribution. And this signals that the decrease in the minima is likely the modest. And it is also possible that some regions or coastal sections, some recordings there already are the maximum possible minimum, or possible minimum. And the estimates of different models clearly separate for different groups, 2 different groups. And to conclude, the nature of extreme water levels may radically vary along the shores of the eastern Baltic Sea. In the eastern parts of Gulf of Finland and Gulf of Riga, the extreme water levels seem to follow fresh distribution, and therefore they may exhibit rapid increase in time. In the rest of Gulf of Finland and at the West Estonian archipelago, the increase is smaller but still existent because of Kumbel distribution. And in the shores of Latvia and Lithuania, the increase of extremes is the slowest because of presence of variable distribution. But this study also indicates that in most of the areas, usage of Kumbel distribution is appropriate to find the extreme water levels in our study area. And for negative values, the 3-parameter variable seems to be the most suitable. And also different methods for estimates of the parameters of the general extreme value distributions may lead to considerably different results. Thank you for your attention.
Thank you very much. My first reaction is that what will happen to this maxima in the future? Do you have any opinion about that?
Well, I can only speculate, but probably it will increase.
Yeah. And how should we take this into account, these extreme events in Tallinn, for example?
Well, if making the coastal planning or city planning, these things have to be considered.
Okay.
Also in Pärnu, I think this is the most dangerous region.
Yeah.
Or endangered.
Okay, other questions? Do I see any hands here? Everything is clear with water level for everybody? This, maybe Tarmo has some comments to this. Pena has a comment, yes, thanks.
I have a very interesting comment actually. I have done a lot of ice flow statistics last 40 years. I came to the same conclusion as you that Kumbel is quite good in some ice load, but viable with 3 parameters is best. So it's interesting. Ice loading and this water level behave the same statistics. Very interesting. Thank you. The same water, of course. So.
Yeah, I do have some comments. So in a way, this seems to be heavy mathematics. But if you take a gymnasium scale pupil and tell how to do that, it's fairly easy, even if it's very scary in some sense. But there are much more deeper consequences, or I would say even ramifications from this analysis. One thing is clear that in some coastal areas you may feel safe. Whatever maxima you have had, either high water levels or low water levels, there is no potential for increase. So our colleagues in Latvia and Lithuania and Upper Baltic proper shore may feel really safe. And some areas, quite limited areas, are such that much higher extremes are expected. Whether it will happen this year or next year or in 10 years, it's debatable, but you shouldn't build close to the coast, no way. This is one thing. The other thing is that different methods for estimates of those extremes give you radically different answers. Which means that if you are going to use some statistical methods, never ever limit yourself to one method. Our experience is that simple thing, estimate of parameters of viable distribution for flow speeds measured by an ADV. If you use maximum likelihood method, you get one result. If you proceed from moments, you get completely different result. The difference is 50%. And if you project that into far future, the difference is absolutely major. So be aware about traps which are provided by single statistical methods. But one more thing which was actually striking, possibly for modelers, we have very few modelers here. The models which we think are almost perfect for the Baltic Sea, they are not. Models mostly which are used for operational modeling, they reproduce kind of moderate water level elevations and depressions really nicely. But most models, I think that even all models which are in operational use today are not able to replicate water level maxima. This is kind of striking message. There is a lot of room for improvement, either models or forcing fields. The RCO model, Rossby Center Ocean model, had very specific forcing fields, and it reproduced almost perfectly maxima in the Eastern Baltic Sea, but failed to reproduce maxima in Western Baltic Sea. And the things are even much worse for water level minima, where we see clear difference in the performance of models, not in terms of, yes, first of all, in terms of statistical parameters, and this shouldn't be this way. So there is a lot of improvement for models still which should be done. So that's actually not a very good message for those who are modeling, but it's a good message saying that there is a lot of research still needed to understand what happens and why minima or maxima are really not replicated.
Thank you. That was like an extra presentation. So, and the next paper is by Vidar Wang and the co-authors about about phase resolved wave modeling at the Baltic harbor. So please.
Thank you very much, Chairman. So this is a continued presentation from the keynote in a way about what we have been doing and what we plan to do in the phase resolved modeling domain with RIF3D. As the professor just mentioned, in the following presentation, there's no water level maxima, so water level is the same, constant. But nonetheless, we'll see a lot of physics still about what's happening in more detail around the Baltic harbors and Baltic shores. So first, we need to look at the Baltic, or like Eastern Baltic region, and what are the characteristics that we're looking at before we dive on into the numerical modeling. So first is that we see actually quite large water bodies. As you can see, I have a laser, is the Gulf of Finland is very elongated water body. So it's quite narrow relatively, north-south-wise, but it's quite long, east and western-wise. So that means actually at least along the east and western direction, we expect quite long fetch. It allows the wind to blow over the surface and generate quite large local wind waves. Even though we're not exposed to the North Atlantic, we probably don't have as huge swells, but we get very long fetch in the west-east direction. So we can expect high waves, in fact, when it's not covered by ice, that is. And also, we look at the water depth. You can't read the numbers, but for most of it, you have a water depth contour near the deepest part at about 50 meters. And only when you reach to the west, close to Gotland, you have 100-meter water depth. So it's in generally about 50-meter water depth. And that's a water depth that is kind of intermediate, but it depends on the wave condition as well. Because when we talk about water depth, it's never only about the absolute depth, but about a relationship between the water depths to wavelength. And since we can expect quite a lot of locally wind-generated waves, so that means we have a large range of frequencies of waves. So it could range from deep water to intermediate water depth. That's the kind of from simulation point of view, what we expect. So that's what means that using pure two-dimensional shallow water model for Baltic region might not be the most appropriate solution. So we need to go a bit deeper. And also, when we look at the coastlines around the Baltic, that's the part I really love about it, is that you have so many beaches. I need to come back in summer and enjoy the beach, because in Norway it's only rocky coast. Here we have a lot of sandy beach. We look at, for example, along the Gulf of Finland, and look at two locations. The harbor at Nassare. You can see the sediment deposition to the north side of the harbor, and a long beach, and you can see the subsea dunes. Also to the east, close to Narva-Juisu, if I pronounce it correctly, you can also see a very long stretch of beach with a river entry right in the middle. Similarly, if we move to the Gulf of Riga, also look at two locations at the harbor at Runo. Again, it's a harbor actually in the middle of a very sandy beach as well. And when we look at, not exactly at the Pärnu harbor, but we look at the Wagrena beach to the north part of the Pärnu Bay, you can also see the formation of subsea dunes. So it's a very sandy beach, which means that sand transport is a very important aspect in all the simulations. So that's also why, following the keynote, why Professor Hans presented the new model, NH flow, to be able to represent the coastal swirlstone dynamics and to be able to include viscosity and turbulence for sediment transport in the future. So you have already seen this slide. We develop our own kind of, basically it's developed by Hansbis and the group at NTNU in Norway. It's open source model for wave hydrodynamics. And yeah, you can actually visit the website and download and give a play. So at the moment, we have 4 different types of models. The CFD model to the left corner, that's very high resolution. So it's not really suitable for such a large domain that we are looking at. The shallow water model to the right corner is S-flow. As I mentioned, in Baltic region, it's actually quite intermediate to deep water condition. So we are not using that model for the Baltic. Instead, we focus on these two models, the fully nonlinear potential flow models. That is very good for wave propagation over a large area with drastic water depth variations. And also the NH flow that has similar properties as FMPF, but in addition, it can also include viscosity, source zone dynamics, and turbulence in the future. So the videos are playing perfect. Oh, is it? Wait. So I just give you an impression of what these two models might look like in real time. So first, the governing equations are different, as you've seen in the keynote. Second, so FMPF is very good at wave propagation and transformation from deep to shallow water over very drastic water depth change. But NH flow, it will be able to, you see the video, look at the coastline area, the waves moving up and down. Like the wave run up above the mean water level and run down. This process in the source zone area is what really makes the NH flow very suitable for the Baltic region, because we need to look at the coastal morphology. So what we have been doing is we used FMPF model, the wave propagation model, for the wave analysis. So wave analysis alone with wave transformations, but not any coastal source zone dynamics. So especially we look at the effects of the breakwaters. As an example, we look at the wave scenario around Nassau Harbor that I presented in IHR last year. And in the keynote, you have seen some of the simulations, so I will focus on the Runo Harbor. At the Runo, that is old harbor layout. As you can see, we have two breakwaters surrounding the harbor, and then we have an intermediate breakwater around in the middle of the harbor. That is where the ferry terminal is located. And we used Jones wave spectrum that took the measurement from our Estonian partners that I took the largest significant wave height and the longest peak period. So it's not the steepest wave, but it represents the largest wave height and longest peak period. And we applied a Mitsuyasu type of directional spreading because it might be wind-generated wave. So it's but I used a very large, so shape factor 28. So it's very narrowly spreading. See, it's almost like swell. And it has about 2 million cells in total in this simulation, and this domain is about 1.25 kilometers in each direction. I run this model for 3.5 hours because in industry standard, quite often we need a 3-hour time series to produce statistical values. So then I give an extra half an hour to let the wave propagate and stabilize. And that took 2.5 hours for us to actually calculate it. At a local machine with 128 cores. So it's actually faster than real time. And with the flexibility of the numerical wave model, we can look at the wave propagations from different directions to investigate, okay, what could possibly be the most dangerous scenarios for the harbor, for example. And then we can also compare the new harbor layout to the right-hand side of the images. Oh, so all of those are with new harbor layout, and the previous slide is old harbor layout. And then we can look at the wave height changes at all wave gauges, 1 to 6, from offshore to inner harbor. And all the dashed lines in the right-hand side upper image, they are from the old harbor layout. All the solid lines are from the new harbor layout. And you can see wave height has been reduced significantly, especially along the navigation channel for the ferry. But also you can see, if you look at the green line, there's a peak at wave gauge 4 that has increased wave height for the wave direction from the southeast, which means that it's the wave direction here. So the wave is coming straight into the harbor, aligned with the navigation channel. So that creates the most dangerous scenario. But also we can look at how the spectrum or how the wave energy is distributing over different frequencies. You can see in the old harbor, shown as dashed line, In the inner harbor area, you have 1, 2, 3, 4 peaks, or almost 5 peaks. So due to the wave interaction and transformation, you have like a 5-mode wave condition in the old harbor layout. But in the new harbor layout, in the inner harbor, you have only 2 predominant peaks. So that actually makes it's easier to design your infrastructure, so we'll consider only 2 primary modes instead of 5 primary modes. So that's one of the studies that we've been doing with FNPF. But with NH flow, we can also reproduce very similar results. That's with NH flow now. And it's also 3D model, so you actually can look at the cross-sections on how the waves are propagating towards the coast. But also, if you look at the coastline, you see a bit whited areas that indicates the wave run up above the still water level. So we can actually look at the swashstone dynamics. This might look a bit weird because I stretched vertically for 20 with a factor of 20 just for visualization. So it's not really the waves are splashing up so high. For another example I would like to show is at also Narva Jusu. Because again, that's a very good example for very sandy, long sandy beach. And also there's a river entry, so you would have additional current and discharge into the water body. So this is the simulation video clip with NH flow this time. And that's the Narva River coming into the coast, and we have also, again, short west wave propagating towards the coast. Because of the natural geometry of the coast, so the waves coming straight from west, but actually it's inclined wave, so the wave approach the shore at an inclined angle. And if you also zoom in a little bit more detail to the coast, you can see how the wave propagates. And if you really focus your eyes on the coastline, you can see the waves run up and run down. Basically, the coastline geometry changes over time because of wave run up and run down. That's also, again, the difference between NH flow and FNPF, because in a potential flow model, the coastline is fixed. But in this model, the coastline is not fixed, so we can have the coastline, coast swashstone dynamics. And you have seen this picture before, but I want to explain a little bit more. It's a very interesting picture when we look at the cross-section, because as we also heard from yesterday, there are longshore sediment transport, there are also cross-shore sediment transport. So now we look at the cross-shore section from relatively offshore towards the harbor. There are many interesting details here you can see, not all relevant to the sediment transport, but if you look at this group of waves, that reminds me of how the Three Sisters freak wave would take place. The freak waves can take place in offshore area, in coastal area. It does not need to be like 30-meter tall waves, but it just need to be way much higher than the surrounding neighboring waves. So in this case, the definition basically is like if you have a wave height over twice that of the neighboring significant wave height, then you have a freak wave. And this pattern really reminds me of the freak wave pattern. I don't know what it is, but due to this bottom bathymetry variations and wave interaction, you could actually have a locally focused waves. That's very interesting to observe in the simulation. Another interesting thing is that you see a belt of higher waves, it's more red when the waves approach the shore, which indicates the surf zone. So a lot of waves will break already at this location, and after this surge of high waves, wave height become reduced. That's because of the dissipation of wave energy after the breaking. And the waves will run up to the shore, and then you reach the swash zone. So that's just a very interesting detail to look at. And so that's more like what we can use it for cross-shore information, because what I showed was x direction velocity, and you can use x direction velocity to calculate the bottom shear stress, for example, once we include the turbulence model, and then you can calculate cross-shore sediment transport. But then also here, I'm looking at the velocity in the y direction. Now you look at the color scheme. Because the waves are approaching to the shore in oblique angle, and also due to the wave transformations, due to the coastline geometry and bottom bathymetry, we do observe quite high lateral y direction velocity close to the shore. So that might indicate wave-driven current, longshore current, that is relevant to what we heard yesterday, wave-driven longshore currents along the Baltic region. And last, about time, a quick summary, why we have an inch flow, because it can have all the wave transformations from deep to shallow water, it can represent source zone. And in future, what we are going to implement is also river currents and sediment transport, including turbulence. So this is also the Narva river mouth into the Baltic Sea, and that's the current day status. And I think they do have the plan to build a new breakwater. So you can have a look at the video. Credit to our Estonian partner, Rin Monicus. He shared this video. So this breakwater is actually kind of abandoned. Nowadays it's not fully in function at the river mouth, and there will be a new breakwater. So we hope to also maybe can contribute in this process, because it's not only about protecting the shipping lanes, but also how do you intercept or change the sediment transport patterns along the coast. Thank you very much.
Thank you very much for this very thorough investigation of the harbors. So we have certainly some interesting questions here. At least I have in the beginning, if you compare this Baltic harbors with some of these Norwegian harbors, you certainly will find some differences. Maybe in Norway it's much deeper, or what kind of channels you have in the harbors. So can you explain if the Baltic harbors are somehow different or not?
Thank you very much. Yeah. That's a very good question. I think there are two probably three main differences between the Norwegian harbor and the Baltic harbor. In the Norwegian area, indeed, because of the existence of fjords and a lot of harbors along the fjords, so the water depth changes. It's more drastic. You can have so almost 45-degree slope, subsea slope outside the harbor. You move out 500 meters, then you already have 500 meters water depth. So that's a very drastic change. But also many Norwegian harbors are more also prone to large swells from the North Sea. Mm-hmm. So you have very long waves that can penetrate deep into the harbor. But the Norwegian coast is very rocky, mostly. So sediment transport is not that predominant. But in the Baltic area, I think that's very important. So the harbor design has to think so much on dredging process, not only how to protect the harbor from waves, but how to protect from sediments and morphology changes. So that's an additional challenge, I think.
And what about the lack of tides in the Baltic Sea compared to Norway?
Yeah, that's also very interesting. Also followed the last presentation. I think that's a relatively new domain for me, for research-wise, also to look at tides, also storm surges, and different mean water level variations. That I think I have to do a bit more homework on that one to answer this question.
Okay, do we have some questions from the audience? I cannot see now any hands rising. People start to be tired, I think, after the party last night. So, but thank you very much for this interesting presentation. And the next talk should be by Jaana Haavisto about should we invest more in research or use resources for additional policies. So, please.
Hello, thank you for the introduction. I'm Jaana Haavisto. I'm from the Faculty of Environmental and Biological Sciences. I work at the moment in the research group of ecosystem and environment in the University of Helsinki, and I will be a soon-to-be PhD student. So I'm presenting my current research on the relationship between value of information and control in oil spill risk management. And the first title, I think, was trying to maybe get this idea to be more understandable in a common sense, but this is the more harder title then. And the agenda for today is I'll be going through the introduction part, then methods and analysis results, and future possibilities. So for introduction, I will maybe give a little bit of insight on the initial ideas that we have between the relationship between research and policies. So if we think about research, it allows us to choose the most beneficial actions in terms of policy implementation. Because as we know, without information, it is very hard to form advised policies or options. We have more uncertainty about the efficiency, the outcome, and also possibly more economic losses. And then with policies, they help us, of course, to reach the most desired state of the system, the outcome that we want. We need policies to get to that outcome. And of course, only knowledge does not result as changes. We need the actions to reach these outcomes that we want. So then without policy implementation, possibly we can't affect the system. So this is kind of the relationship between knowledge and policy implementation, information, controllability. And this is, of course, the question for the policymaker as well. For example, in ministries, they need to decide on allocating resources between policy implementation and further research. And how to do that, that can be very hard to tell. How should the allocation be then? There are, however, only a few published papers looking at this relationship between controllability and information. One example is the paper by Fenwick and others who modeled the implementation of new healthcare technology and tried to include what we have in real life, that policy implementation is not perfect. We can't have perfect policy implementation. Usually that's not the real life. But in modeling analysis, that is what we assume, that the policy implementation is perfect and immediate as well. So then my research questions were to explore the relationship between value of information and value of control. And in my case, I tried to do that in Bayesian influence diagrams. And then to have kind of ideas how to advise with these results, the implementation or the allocation of resources between policy implementation and information. So, like I said, I used Bayesian networks or so-called influence diagrams to analyze this. Bayesian networks, they are causal probabilistic networks. They consist of these random variables called uncertainty nodes and then arcs between them that tell about the hierarchies or dependencies between the variables. And the variables contain information in kind of probability distributions in a form that can be consisted of current data or expert knowledge or simulations. And then influence diagrams are similar to this, but they also have additional nodes for decisions and then utilities. So influence diagram as a name is quite good, as it tells us how this decision will influence our utilities in this network. And then I used this published Bayesian decision model by Helle et al. To my analysis. It is a cost-benefit analysis model that consists of two management policies, one of them being automatic alarm system that is a preventive pre-spill policy, and then the other one is new oil company vessel, which is a post-spill policy measure. Here is the model. In both of the corners or upper corners, we can see the decisions. The green ones are the costs, and then there are also this external damage function, which describes the environmental benefits of not having oil in the Baltic Sea. And then the blue one in the left upper corner is what I introduced in this model. It's a uncertainty node for the implementation of this alarm system. According to this network, the alarm system is the most, or is the cost beneficial policy implementation that should be chosen. So that's why I wanted to include this uncertainty to this policy decision to see how sensitive it might be to the introduction of different policy implementation uncertainty levels. And then value of information, of course, it tells us how much we gain if we know or we could observe the true state of variable before making the decision. So then value of information basically is it is calculated with the expected maximum value, which is the knowledge with the uncertainty, and then with perfect information. So it is the difference between information under perfect certainty and uncertainty. And then value of control in this is modeled with uncertainty. Or, of course, if we would, well, let's say that we have the uncertainty in the outcome of policy. So in this case, in this model, it is the annual number of collisions after we implement the alarm system that we are looking at in this case. And from the previous research, which has explored the possibility of perfect controllability and how that affects the value of information, if we have better control over the outcome that we want, then value of information decreases because we don't need any more of information because we already have the higher probability to reach the outcome that we want. So I wanted to explore what happens to the value of information when in real life we don't have the controllability that we assumed to have based on previous knowledge. So to do so, I introduced the uncertainty between the decision and the outcome, and I used two approaches for creating this uncertainty because in the probability distribution, the uncertainty is, well, it is based on these two approaches, how to allocate the probability to the distribution more evenly so that it is more uncertain. So the first approach is then the proportional covariation method, and it deducts the probability mass from the most probable option, which is in this case is 0 accidents, and then allocates it between the other scenarios, which are 1 to 6 accidents per year, based on their proportional sizes. So with this method or approach, then it distributes the probability mass mostly to 1 accident per year, because proportionally it is the more probable outcome to happen. Which of course, it's what I wanted to do is look at the effects of no control in value of information. So this does not approach this no uncontrollability, because we still have some information in the probability distribution. And then the second approach to reach the uniform or uncontrollability in the probability distribution, I use the uniform covariation method that is order preserving, so that maybe we could better see how this no control or information, how that affects the need for further information. So then for results, or maybe I explain first. So the results are then conducted for each level of uncertainty, which are between numbers 0 to 10, 0 being no added uncertainty and 10 being then the maximum uncertainty. And for both approaches, the proportional and the uniform. And then with only the alarm system, without the possibility to having the other policy option, which is the vessel, in the analysis as well. So first only for the alarm system, and then having both of the decisions in the analysis as well. So this is value of information results for the first approach, which was the proportional covariation method, and then without the possibility to observe new vessel in the analysis. So we can see that we don't have value of information with only the alarm system, and for this method only for the highest level of uncertainty, which is mostly that we have one accident per year, and that we can't really control it. So this does not then maybe represent the no control in the distribution, like I assumed as well. So the value of information increases for the higher levels of uncertainty. And then for the uniform distribution or covariation method without the new vessel, we can see that now value of information starts to increase in level 2 and increases all the way up to level 9, and then decreases to 0 when we have the uniform distribution. So if we don't have the control, we don't really need the information in this according to this result. And then this is for the, again, proportional covariation, but now we have both policies in the analysis. So now we can see the optimal policy decisions in the blue area. In this case, the alarm system is always optimal, and the new vessel has been unoptimal from the beginning. But now we can see that first, if we look at the value of information, it increases to the point of level 3, and then decreases after that when we go to level 4. And this is the point where we also implement the new vessel. So the need for, or how the information in this point after this certain threshold, it cannot anymore support this decision to only implement the alarm system. We also need the other policy option as well. So then our need for further information decreases. Of course, now there is value of information from the new vessel as well, because it is included in the analysis, which we can also see that now that we, in this uniform covariation method, in this case it doesn't decrease to 0 because we have the new vessel in the analysis as well. But now we can see that the kind of shape is similar than we had in the previous results, which is that after certain point, value of information first it increases and then starts to decrease, and the optimal decision is to implement the vessel as well. And I am running out of time, but so to conclude these results is that, of course, these are methods to maybe include the possibility of implementation uncertainty that is in real life. Our policies might not present like we hoped for. So what does that then do to our the optimality of other decisions or the need for further information, and in what variables? So testing this models with the implementation uncertainty can be beneficial then. And for future possibilities, of course, now that with Russia's actions in Ukraine, we can see that we have more uncertainty in the Baltic Sea regarding new unknown vessels going around, and maybe, or I would say we have more uncertainty, of course, in the effectiveness of our current oil spill risk management policies as well. We don't know anything about these tankers, and that, in my opinion, increases our risks of maritime oil accidents. So then, of course, that should be explored in the modeling as well. And then what has been discussed earlier in years today was the improvement of scientific cost effectiveness through cooperation in the Baltic Sea, and the possibility of including these benefits and costs in modeling as well, I think should be discussed more. And for me, the testing of these methods will be also in different types of influence diagrams, and then, of course, more analysis about the effects on different variables that we need more information about, and the sensitivity of these variables to the uncertainty. And then, of course, the possibility to include, or how could we include the relationship of businesses in this case? As also mentioned yesterday, businesses can be a beneficial provider in the research funding. So how these benefits of research to the businesses, could that be modeled as well better in our analysis? And okay, that is from me this time. Thank you very much for listening. And
thank you very much.
Thank you.
Time for questions. Pentti.
Well, first of all, thank you for the presentation. Thank you for using our Bayesian model, because I was also involved in to make the model 2015 and Helle published. So it's very nice that somebody will continue the work. So I have maybe some difficult question for you. If the uncertainty is so important parameter, how we can affect on to make uncertainty small?
to make uncertainty smaller.
And how we can affect to uncertainty, because it seems to be very important parameter in the, it's very important, so how we can affect the most important parameter, uncertainty. It's a difficult question, I know, but let's see.
That is the good question, thank you for that. Well, research, of course, with knowledge, we can decrease the uncertainty. But then, of course, we need the actions there as well. How can we only decrease the uncertainties with knowledge if we don't know how to, or do not implement this information into action and do it effectively as well?
And very good luck for your doctoral. I wait for the doctoral results. It's very important topic what you're doing.
Thank you.
More questions? Actually, I have one question which was related to this Russian oil spill. Possible oil spill. So could you tell something more about these risks? I don't quite understand if you think that the risk is increasing and why, if it's so.
Well, the risk for possible oil spills.
Yeah.
Of course, there can be multiple risk increasing factors. In this case, with the process actions and how we have more unknown tankers going on that have they are not so in good condition, possibly, but we don't know. We don't know basically anything about them. So that's the uncertainty, I think. How are then our current pre-spill measures? Are they affecting these unknown tankers as well? So that, in my opinion, increases the risk for oil spill catastrophes in the Baltic Sea.
Okay. I hope that our decision makers also are aware, or the politicians are aware of this situation. Okay, do we have some other questions still? I don't see now any hands. Thank you for this very interesting presentation again.
Thank you.
Now we have come to the final talk by Aivo Lepland and a number of colleagues, seafloor iron, manganese, precipitates and pockmarks of the Gulf of Finland, formation control and possible genetic links. Please.
Yes, thank you for this introduction. Thanks everyone for sticking around until the bitter end here, and also thanks Tarmo and Margit and gentlemen at the back running the show so smoothly here. So this has been an excellent meeting with the excellent organizations. Thanks for that. Okay, so here I go then. The last presentation of the meeting, long-awaited moment. Yes, so I'll talk about the precipitates forming at the seafloor in the Gulf of Finland, but first I say something more general about the uniqueness of the Baltic Sea. And if we look at this figure here, which shows where various types of autogenic precipitates, this means that the minerals that form at the seafloor or in the shallow sediments occur in the Baltic Sea. These dark areas on this map, they're showing the positions of Landsort, Gotland, and Bornholm basins are the anoxic deeps of the Baltic Sea, where reduced iron and manganese minerals form. These are sulfides and carbonates. And in the more shallow areas, we have the precipitation of these oxo-hydroxide type of phases. And the Gulf of Finland is one of the hotspots when it comes to these oxide precipitates. If we zoom now in towards the central part of Gulf of Finland, around the Estonian island of Vaindlo, which is about 100 kilometers east from here, and then at the right-hand side we have the bathymetric image of the seafloor, the green and reddish colors showing the areas of the shallower waters, and the blue areas showing the areas of the deeper water. Then in this area of the Gulf of Finland, central Gulf of Finland, we see that the seafloor is highly variable. In the northern part, where we have this rough seafloor, this is where the bedrock, crystalline bedrock, exposing right at the seafloor. Whereas if we come further south, the seafloor gets more smoother. That's where there's a more sediment deposition. But again, there are these ridges and depositional areas closely spaced together. And on the left-hand side, we have this greenish map showing the distribution of these iron-manganese oxo-hydroxide precipitates that have been documented during previous mapping programs that the Estonian Geological Survey has been spearheading. So yes, so we see that there is a huge amount of concretions, huge amount of these manganese nodules in some areas, but the distribution is patchy, and they occur only in the areas where there is no modern deposition. So no modern deposition, so that the bedrock or the deposits that were deposited during the glacial times are exposed right at the seafloor. So, and if we zoom now in to this red square shown on the bathymetric image at the right, there we see a submarine ridge. The bathymetric image is again on the right-hand side, and this submarine ridge has a length about 3 kilometers and the width about half a kilometer. And if we look closely into this submarine ridge, then we see that there are these holes in it. So this is like a Swiss cheese on a seafloor. And these holes, this is because of there's some sort of fluid coming from below and generating these holes for us. And these are carved into these late glacial deposits that were accumulating in a basin some 13,000 years ago. And so what do we see within these depressions, what we call pockmarks, and around them we see these whitish, brownish microbial mats together with the seafloor precipitates. And if we take a sample from it, then what do we get? We get these various morphological types of crusts and nodules. Very beautiful materials for studying. So yes, I've impressed my wife with that. So, but if we have had chance to go down onto the seafloor and see what's really happening there and how these microbial mats and the precipitates that are forming are interlinked. And so this is the collaboration with our Norwegian partners from NTNU. So you guys, this is the NTNU ROV that we brought here to Tallinn in August, and we had the great privilege of using it and creating great information about the seafloor. So if I run that, and so that here we are within one of these pockmarks. So left-hand side we have these 2-meter escarpment of carved into the barred clays, and in front of this escarpment we have these beautiful microbial mats forming there, telling that there are some reducing fluids coming up, possibly reaching methane, giving rise to the mats of sulfur-oxidizing bacteria forming at the seafloor. So this is what we see within these pockmarks. So that beautiful features, nice vertical escarpments, excellent field geology you can do at the seafloor. But if we go a little bit away, so that's what we see is the seafloor covered by these precipitates. Nothing else, just a layer of precipitates. Tightly together. So there are various types. Some of them are more crust-looking. Some of them are more like nodules. But yes, many areas of the central Gulf of Finland. That's what we have. Isn't that fun? So why do we have these pockmarks and concretions forming on the seafloor? So if I look at little bit deeper, what is below the seafloor, and this is the seismic profiling done by the Estonian Geological Survey across the submarine ridge, a little bit west of the island of Vainlo, and the upper panel shows the unfiltered raw data that are obtained by the seismic profiling, and the lower panel tells us about the interpretation of these seismic profiles. And the lower unit, this is the bedrock, this brownish-looking unit, this is a bedrock. In the middle of the ridge, we have a yellow unit on top of it. This might be another type of sedimentary rock, or could be glacial till. We don't know. We don't quite know exactly. But then on top of it, there is this blue layer, which is about 10 meters thick, and this is the. Is there something wrong? No. Okay. I'm sure. Anyhow, so we have this 10-meter layer draping the pre-existing seafloor. When there is a topographic high, the blue unit makes also the high. When there is a topographic low, blue unit makes also a low. And this is a typical for the deposits that were depositing in a basin in front of the ice sheet. These are these so-called varged clays. Glacial lacustrine clays, so that this is the snapshot of the area of about 13,000 years ago, when in front of the ice, there was still ice in Finland, so that you guys our Finnish colleagues had a little bit colder times than us at that point of time. But here we had a big body of water, and then this big body of water, these clays, ward clays, ward because they consist of the sandy layer and the clay layer. The sandy layer corresponding to the melting during the summer, and the clay layer corresponding to the more general melting throughout the years. So that these ward clays accumulated all over the Gulf of Finland and huge parts of also the other parts of the Baltic Basin, and put this 10-meter blanket to the seafloor. And this 10-meter blanket is really rich in clay, so that if we have some fluids coming from below, they are stuck. So they would try to find a way out and try to find the weaknesses, and then they migrate towards the topographic highs where they punch through. And that's how we form these pockmarks, which occur in many different places, but are really common on the topographic highs where the ward clays are exposed there. Okay, so that we have some sort of fluid control mechanism, which is dictated to some extent by these ward clays, by 10 meters of the clays that are blanketing the basin. But where do these fluids come from? Well, if we look at this image here, and which is the product of the European Union program EMODNet, and showing the various marine minerals in different parts of the Europe, I zoomed into the Baltic Sea with a focus on the Gulf of Finland. Then we see that the eastern part of the Gulf of Finland is really rich in these polymetallic nodules. That's where they occur in a huge abundance, really, eastern part. So what's the big deal about the eastern part of the Gulf of Finland? What's happening there? What is the geology? Is there some sort of geological control behind it? So if we now add the geological map here, so I'm sorry, might be a little bit too much of the geological information. I did certainly something wrong.
Okay, I just wanted to move with you.
Oh, yes, I messed it up again. Okay, I don't know how this is going to go. Yes, so this is a geological map. The pink colors, they apply for the crystalline rocks of Finland. As we come southward, we have the cover of sedimentary rocks on top of the crystalline basement. And this grayish-looking unit at the eastern part of Gulf of Finland, these are the sandstones of the Ediacaran period, about 550 million years ago. And these sandstones, they thicken eastwards and have their outcrop, not outcrop really, but subcrop in the eastern part of Gulf of Finland, in the very same area where these manganese oxide, where these nodules occur. So that could there be a link that these Ediacaran rocks, the porous Ediacaran rocks, which can carry a lot of fluids, could be the source of fluids that bring us the dissolved manganese into the marine environment, and then it gets reprecipitated on the seafloor. We don't know, but there is this geological coincidence. What we want to figure out in a greater detail. But why there should be fluids in these Ediacaran rocks that want to leak out? Well, how do I do it? Yes, so this is there's another piece of geological information, geological cross sections from the Gulf of Finland southward, and then this yellow unit there on top of the pink rocks. This is this Ediacaran horizon, which overlaps in its subcropping area with the occurrence of these manganese nodules. So could this Ediacaran sandstone be leaking and give us all the fun that we have at the seafloor of Gulf of Finland? Well, it's kind of interesting, but if we also consider the recent, more recent geological history during the glacial times and deglaciation, then when we had the ice at its maximum 25,000 years ago, we had 1,500 meters of the ice on top of whatever substrate was here, and this was generated quite some extra loading for the underlying strata and could generate in these aquifers extra pressures which were released then when the ice was taken away. So, and then the question is, do we have some indications when has the leakage been occurring, and how can we time constrain it? So, and this is when when these concretions come in really handy. So this is one of the concentric concretions going layer by layer by layer. We want to really open their birth certificates. So we want to know when they were born and how long they were living. Well, we are working on these radiometric dating of these concretions, but we don't have the answers yet. But one of the answers could come from the stable isotopes. The stable isotopes, organic matter that are embedded in, during the precipitation period. And if we look at the graph at the right there, so that organic matter that was deposited in the Baltic Sea basin during the late glacial times is significantly different from the organic matter that deposits in a basin these days. So that, yes, so that's a 2-3 promille difference, so that the late glacial deposits contain organic matter with values of -27, and whereas the modern organic matter is about -23 or even 23, 24, depending where we are in the Baltic. And if we look now in what kind of organic matter is embedded in the concretions, then we see that in some of the concretions in the middle part we have these -27 numbers, and these 27 numbers are then typical for the late glacial times, so that it might well happen that we had a pulse of the initial growth of these concretions already during the late glacial times. There was possibly quite some fluid movement then, as a Baltic Sea ecosystem was trying to establish the equilibrium with a new situation of deglaciation, and then the precipitation continued a little bit later, or quite a bit later, as well as some of the concretions contain organic matter that is typical for the modern Baltic Sea. Anyhow, so there's still a lot to do, and we have this international team here and many students involved, and we have been putting in proposals for the different funding sources. The funding scheme Water for All that was mentioned yesterday is one of the targeted funding sources. But so what do we want to do? We really want to do the geologic and hydraulic context of the nodule formation, what we want to get a handle upon. We want to know the sources of iron and manganese. We want to know the controls of precipitation. We want to know the timing and tempo, associated microbial processes and consortia, their economic potential, and also what needs to be assessed is the environmental aspects that connect to the stability of nodules. And then I come to the last slide here, and this is the troublesome aspect. So that we have these beautiful seafloor features in the central Gulf of Finland, and we know that we've been discussing that there are these oil tankers parking in the middle of the Gulf of Finland, exactly where these beautiful seaflow phenomena are occurring. And it's not really know how they influence the seafloor. Of course, they are really doing the damage. There's no question about that. So that we can call it geovandalism. But there might be environmental consequences as well, as these iron manganese precipitates on the seafloor. They are real sponges for the phosphate. They are sponges for the range of metals. And if the anchoring, the disturbance of the seafloor stirs up the seafloor, and these iron manganese concretions happen to be in an environment where they become unstable and can be reductively dissolved, we may have the environmental problem on top of all the political issues as well. So that's what we want to kind of collaborate with across disciplines, and as I said yesterday, work out the best ways to take care of and manage our unique resource, which is the Gulf of Finland.
Thank you very much. So, any questions? Pentti.
Well, thank you again. Very interesting presentation. We were studying iron manganese in early 80s. It was a very hot topic when I was a student, actually. Yeah, but not in the Gulf of Finland, but somewhere outside south. But my question is, any idea about the economic value of this iron manganese in Gulf of Finland? Is it any idea about, should I buy a boat and start getting them out? Or?
Well, when it comes to their economic value, and then if we put these concretions into the perspective of the deep sea mining, so that there are plans for mining these type of concretions in the Pacific and in the Indian Ocean, and in these oceanic basins, these concretions have been growing over millions and millions and millions of years, whereas in the Baltic Sea we don't have this luxury. They were born when the ice retreated from the area, or they started to grow then. And in the deep sea concretions, the main catch is cobalt. The cobalt is really the economic resource that the companies are trying to get out. The cobalt concentration in the Baltic Sea nodules is relatively low, so the different scavenging mechanisms so that haven't really allowed the cobalt to be enriched in economic quantities. What Russians have done, have tried to use them as a manganese resource, but these things need to be evaluated properly. So yes, I can't answer the questions. I'll write into the letter I sent to Santa, perhaps, yes. Some answers.
Are there some other? Arno Kotilainen will ask.
Thank you, Ivo, for a very interesting presentation. Dealing with those pockmarks, do you think so that those, as you said, been active since the declassiation all the time, or?
No, I think they are dead pockmarks and they are live pockmarks. So they are these beautiful active pockmarks which have these vertical walls, even negatively tilting walls, and then we see the band of microbial mats right at these walls, telling that something is pressing up from there. But then there are these pockmarks that have lost the steepness of their slopes, and then we don't see this kind of active microbial activity in them. So they are active ones and they are dead ones.
Okay, thanks.
Yeah.
Okay, other questions? At least now we learned that the best time of the Estonian history was that when the ice had already melted in Estonia and Finland was still under the ice.
Yeah, well, you are following it.
Yes.
Yeah. That's
yes.
good. I didn't put you to sleep right away.
Yeah, no. Okay, thank you very much, Ivo. This was very nice presentation.
Thank you.
Now we have come to the end of this conference. Before I give the floor to Mr. President, so I want to thank everybody who came here, and of course we should give a big applause to the Estonian Academy, Tarmo, and the angels who did all this for us. So thank you very much.
And now the final remarks from the very biased view of academy. First of all, I'm happy that we invented a new word here. This word was demonstrated in the very first presentation, and it sounds forecat. I think it has much deeper structure and meaning than we think. Remember, Norbert Wiener told now, I think, some almost 80 years ago, that the best material model of a cat is another cat, but preferably the same cat. So forecast is kind of one version of cat. So this perception has been in place for 70 years until in 2016, Claes Gustafsson in journal trends in biotechnology told that, no, that's not correct. The best material model of a cat is several cats. This has been used in marine science for decades. It's called ensemble approach. So a lot of 4 cats gives us a good model of what happened on the sea. Trying to be now slightly more serious. So the focus of this conference in 10 years or so, or even longer if you think about the long history of cooperation across the Gulf of Finland and along the Gulf of Finland, it has been severely moved from mostly biological aspects and water quality monitoring, which was focus some 15, 20 years ago. It has moved, I would say, back to fundamental research, not only hydrodynamics, but also history and future of pollution, and also including many, many governance issues. And the level of generalizations of most talks is also different from those which we used to listen about 10 or 20 years ago. So we are really addressing interactions, not only on words, not on buzzwords, but many talks were truly transdisciplinary, looking at waves interact with the coast, not yet feedback from the coast back to the waves, but a little bit. Interactions of ships and ice and many other things of this kind were interactions of completely different categories and entities have been analyzed and with some quite interesting conclusions. What is also kind of noticeable trend is that the professional level of presented technologies is gradually increasing. So it's not simply measuring and then drawing a nice colored picture and saying that's the scientific result, but going deep into the structure of things. The range of topics addressed in this conference, I would say, is more or less exponentially widening over the years. And with one very clear feature, not a bug, we see nice and straightforward applications of hardcore science. This pool of presentations, it clearly predominates over what was not a feature, but still quite largely present in this conference in the past, which I would call simple calls for being more nice to the environment. We have seen another development in terms of attempts to quantify non-quantifiable. Not only particular items and issues, but systematic attempts to quantitatively address things which have basically qualitative nature, and things which have been always thought to be non-monetary, they still have a quantifiable value. We have seen how advanced metrics is applied to different processes in the sea. Relatively new topic, I think, first time in this series of conferences is noise, how to quantify it properly from the viewpoint of living creatures in the marine environment. Coastal dynamics, which is kind of not a problem for the for Finland, but it is a problem for the rest of the northeastern Baltic Sea. And those advanced metrics have also one common feature. They are targeted to clear and straightforward applications, not of academic interest, but they do contribute to the well-being of the sea and also to marine nations. We see another trend that several fields of science which were on top agenda in the past have now been transferred into monitoring activities, which means that science is advanced enough to make those things manageable and to make clear that many things can be affected also positively by mankind. So science has not get away from those fields. I think it's still there. It's waiting, it's asking not what we should do or what the situation is, it's asking how we should do towards improvement the situation. So we do have the quantification of many things. We have understood the driving mechanisms and we have understood the impact and reaction chains. So science is there for, I would say, waiting either major changes or regime shifts to occur. And if that will occur, then the science will be waken up for those fields. But still, I think that this is a clear indicator of science, of what science has done for society. It's not a problem that some things have moved from science to monitoring. It's a big win of science and scientific community. And I think that this is the natural way of development of science. When some things are absolutely clear, it's just routine. To close, we thought about organizing a competition of posters. But then I saw that as a chairman of the jury that I'm biased towards one poster. So we decided to skip this part of scientific conference, but I still call everybody to look at those posters before you leave. And before you leave, there is still one item in the program, which is light lunch, just behind my back. Thank you very much for investing your time. Thank you very much for your contributions to this conference. And next time, approximately in 1 year. Thank you.